As aircraft gunners, we have to hit a rapidly moving target. We work on the assumption of a straight course, constant speed, and constant height during the short time of the shoot. Now this time we'll shoot. Notice the result of firing directly at the target. Result, a miss. It's a long way behind because we didn't allow for the movement of the target during the time of flight of the shell to P. Now we'll point our gun at F and try again. Missed it again. The plane's got a new F. Obviously the shell took longer to get there this time, so the plane had time to get further. We pointed at F and only allowed for the time of flight to P. By firing the gun in different directions, we could make shells reach the line from P to F at various points, each taking a different time. The job of the predictor is to choose a point which will be reached by the target in the same time as the shell. Now we know all this, let's have another shot, leaving our gun pointing to our new F. We've missed, because we forgot about gravity, so we allow for this by adding tangent elevation. Let's put in TE. That's another thing the predictor has to do. From the time of flight, it can also tell us the correct fuse, so that the shell bursts at the moment of reaching the target. So much for the gunnery problem. Let's look at a model of a bit of countryside. We'll orient ourselves. We'd better look at this from various angles, so that you'll not lose yourself as we go on. Here it is from above. Another point of view, edgeways. This is us at O. Here's a plane. Let's stop it at P. That's its present bearing, BP, the bearing to a point directly under the plane. Here's our present angle of sight, SP. You can see better like this. As we've seen, to hit the target we must lay on a future position F. So that the shell and target take the same time, T, to get there. Don't forget we work on a constant height. The bearing of this future position we'll call BF. The difference between our present bearing and our future bearing is called lateral deflection in azimuth. There it is, dA. Looking straight down, it's evident that BF equals BP plus dA. Now let's think about angle of sight. The future angle of sight is SF. Notice how it differs from SP. This difference is called true vertical deflection and is written dV. This time we look at a dead side view, and it's evident that SF differs from SP by dV. dV may be minus or plus. It's minus in this case. If we can find dA and dV, we know enough to hit the target. Notice that the value of dA depends on time of flight t. The value of dV also, of course, depends on t. This side view shows it clearly. Let's look again from above. This time we are going to deal with the rate at which BP is changing. Here it is going slowly, and after time t, a small dA is produced. Look again. Here BP changes quickly. A large deflection is produced in the same time t. The amount the angle changes in a unit of time is the lateral rate, omega A. In the same way, the vertical rate is omega V. It is the rate at which the angle of sight changes. You can see that dV depends on omega V, as dA depended on omega A. Let's consider dA again, and turn our plane into a car and look down on it. The car moves at an even rate, so the bearing to it changes the same amount each second. There are its omega A's. In 3 seconds, it's gone 3 omega A's. And in t seconds, it has changed t omega A. Nice and easy. But to get this result, he had to travel in a circle. Let's make it go straight. Look how big its omega A was here, and how small there. Evidently, in this case, t into omega A would give us the wrong answer, because all these omega A's are different. We really want the average omega A, but we actually measure it when this target is at P. Mathematicians tell us that instead of dA equals t omega A, we should write sine dA over t equals omega A into tan SF over tan SP. This is, in effect, multiplying the average omega A by t. In the same way, we talk of dV, it can be shown that sine dV plus psi over t equals omega v into sine SF over sine SP. But in this case, we have something new, psi. What is it? Don't bother about it. Just notice this is made up of things we've already dealt with. That is, dA and SF. And we'll go on calling it psi. Here again is the equation dealing with dA. In these two equations, there are various unknowns. Let's see how the predictor utilizes the known quantities to find these unknowns, and so get the answer to the problem. Here's how the predictor number 1 deals with the problem. It measures BP by laying for line. Here's number 3 doing so. He's also getting omega A by his rate of following a moving target. Number 5 gets the present angle of sight by laying for elevation. At the same time, he gets the rate of change of the angle of sight, omega V, by following the moving target. T is found by number 4, setting the pointer of his time drum on the curve of height obtained from the height finder. The drum is turning through SF. Let's see in diagram what these chaps have been doing. Number 3 lays for line. This gives BP. Number 5 measures the angle of sight, SP. Here's the height ordered. Number 2 is having a shot at putting in DA. He hasn't got it definite yet. His rate isn't balanced. Here's his fuzzy effort on the landscape. Number 1 is having a shot at putting in DV. He hasn't got it quite definite. He doesn't know where he is either. Don't forget number 4's version of T is still an experiment. We still don't know SF, which turned his drum. When all these people are working correctly together, no more fuzzy lines, we've got a definite answer. The answer being DA, also DV, giving BF and SF. There's another complication, wind, which upsets everything. We'll put it right by setting in wind. At the top is the circular height scale for wind, and there's where he sets in wind speed and bearing. As a result, the predictor works out a new false future position, so the wind will blow the shell onto the target instead of off it. The time drum is turned through a new SF, so number 4 must move his pointer to a new time. This means new deflections, so the rates will be different. Putting in wind also turns the TE drum through a new SF and moves it up or down to alter TE and height. Look at the fixed pointer at the bottom and the height correction scale. 6 reads the height correction and orders it to 4. Who applies it? 6 does so himself. And they all go on with new data to get a practical solution of the problem. We've shown you the method. Now we'll look inside and see how these things we've been doing connect up with the mechanism. We'll deal with the mechanism for getting DV first. Number 5 lays for elevation. In doing so, he gets present angle of sight, and the rate he has to turn his hand wheel is omega V. Here's a simple drawing of the result of what he's doing. This shaft is moving through SP at a rate omega V. We want these in different parts of the instrument. Meanwhile, number 1 turns his hand wheel an amount proportional to dV. We'll tell you how in a minute. Here he goes. Here's dV. We'll take it over here and bring in SP, which you remember we've already got. dV and SP are added together at this differential, giving us SP plus dV, which we've shown you is SF. This SF shaft turns the time drum through SF. Meanwhile, number 4 is keeping his pointer on the curve of height given him. He winds his pointer down through time of flight, t. We want this t to use in our calculations. Here we are with t and dv. At the same time, lateral rate is being set in elsewhere, as you'll see later. So we have dA, which is needed to make up psi. These three are all combined by a combination of cams, triangular linkage, and a ball and disc drive, driven by the so-called clock, actually a constant speed motor. And the result is sine dv plus psi over t. This is a rate. It's one side of our elevation equation. We told you that number 5, by following for elevation, turns his hand wheel at a rate which gives us omega v. Here is omega v. He also produced sp, which, added to number 1's effort at dv, gave us sf. Another triangular linkage and a ball and disc mechanism produce sin sf over sin sp multiplied by omega v. This, as we've shown you in part 1, is the other side of our elevation equation. This is also a rate. Here are the two rates the instrument has produced. If we connect them through a differential and the crown wheel moves, the two rates are not balanced. The equation isn't solved, something's wrong. The only man on the vertical side free to alter anything is number 1. He isn't following a target or a height curve. If we gear a pointer onto the crown wheel, number 1 can see if it moves, and so he can turn his vertical rate hand wheel a bit more, or a bit less, until the pointer is steady. That is, to steady the pointer and solve the equation, he's got to put in the correct value for dv. This balance can only happen when all the unknowns are correctly evaluated. The equation is now satisfied. The predictor has given the right answer for dv. Our next job is to get QE, which you remember is SF plus TE. We've dealt with numbers 1, 4 and 5. Here's number 6, following on the TE drum, the height curve ordered. We've already shown you the time drum turning through SF. We'll use this motion to turn the tangent elevation drum through SF. Now for what number 6 was doing. By winding his pointer down to the height curve, he sets in the appropriate TE. Now we've got TE and SF, we must add them together and we get QE. This shows on the QE dial and is transmitted electrically to the guns. So much for getting QE. And for the elevation side, our next job is to deal with the bearing or azimuth side. We start with number 3 laying for line. In doing so, he gets present bearing, and the rate at which he turns his hand wheel puts omega A into the instrument. Here's the result of what he's doing. This shaft's moving through BP at a rate omega A. We'll use omega A and leave BP for a moment. The other side of the instrument is, you remember, grinding out SP and SF. These are turned into tan SF over tan SP and multiplied by omega A, the result being a rate, which is one side of our azimuth equation. Meanwhile, number 2 turns his hand wheel an amount proportional to dA. You'll find out how he knows this in a minute. Here's the dA he's putting in. We'll move it over to a triangular linkage, where T got by number 4 is combined with it. This produces an amount, sin dA over T. This amount is turned into a rate by a ball and disc drive driven by the clock. So we get a rod turning at a rate sin dA over t. This, you remember, is the other side of our azimuth equation. Below it we have the rate we found just now. These are the two rates which the azimuth side of our instrument has produced. As on the dV side, we connect them through a differential. This is connected to the lateral rate dial. Number 2 adjusts his dA to steady the pointer, so he is compelled to put in the correct value for dA. The azimuth equation is satisfied. Our next job is to get BF from this dA and BP. We left BP just now sitting here. We need this to get BF, so we'll take it over here. dA we have also got. One thing more. Time, which we have already found, gives us drift, which is dependent on time. This is subtracted from dA. The result is now added to BP. The answer is dA minus drift plus BP, which is BF. This answer is shown on a dial and is also electrically transmitted to the guns. We have now given the guns two of the things it needs, that is, QE and BF. What about fuse? Time obtained from the time drum is not the same thing as fuse. The difference between these two is incorporated on a three-dimensional cam. You learned the principle of this in mechanical maths. If this is rotated through SF, obtained from the TE drum, and moved along according to time, the follower will be pushed out for fuse time difference. This amount is added to the time of flight, T, by a special linkage, to give us our correct fuse setting. This fuse setting is in its turn transmitted electrically to the guns. There you are, future QE, fuse and bearing.